In this video, we will start with a new chapter on acids and bases. Hopefully, some of the material we cover will be a review from general chemistry. We will start with the Branstad and Lowry definition and move on to the Lewis definition of acids and bases, along with looking at the arrow pushing mechanism for acid-base reactions. From there, we will take a quantitative approach at looking at acid and bases, looking at things like pKa's, and lastly, we will see how we can use the pK values in a laboratory setting. We'll go ahead and start our discussion with the Branstad-Lowry definition of acids and bases. In this definition, we are focusing on the proton, the transfers of protons. And as a reminder, a proton is a hydrogen atom without the electron, so it's an H+. And in this definition, an acid is a proton donor. It gives away a proton. And a base is a proton acceptor. It receives that proton. Let's take a look at an example, hydrochloric acid reacting with water. Taking a look at this equilibrium, focusing on the difference between the reactant side versus the product side. We see with the progress of this reaction, the hydrogen highlighted in red is transferred from the HCl species into the H3O species on the product side. So HCl donated its proton, so we would call it an acid. Now in a reaction, if one gives, then another must receive. If HCl gave away the proton, then water, the other reactant, must be receiving that proton. So water in this case is the base. So when the acid and base on the reactant sides reacts, it gives us our product. Now our product will also have a name. What was the original acid after reaction will be called the conjugate base. And what was the base after reaction will be called the conjugate acid. They are called this because, for example, if you go in the reverse reaction, the Cl- will receive a proton to become HCl. So that's why it is a base, because it receives, it accepts a proton. Whereas the H3O+ gives away its proton in that process, therefore it acts as an acid. We just add the word conjugate in front just to signify it is on the product side. Now in this example, we see that water acts as a base. However, water can also act as an acid, and we will see this as a very common occurrence that water can be both an acid and a base depending on the situation. There's a term for this, it's called amphoteric. Let's see an example where water acts as the acid. In this example, we have NH2 anion reacting with water. Let's analyze to see how the reaction has progressed. In this case, the NH2 anion will act as a base as it abstracts the proton from water to form NH3. So therefore, water in this case acts as an acid, and the NH2 anion is the base. On the flip side, since water is the acid, its conjugate is a base. So the OH- anion that's generated is the conjugate base, whereas the NH3 molecule is the conjugate acid. At this point, I also want to point out that when you start out with a negatively charged base, you must be accompanied by a positively charged species to have a neutral compound. And this positively charged species is called a cation. Common cations are the group 1 metals like sodium, lithium, and potassium. So sometimes you may see this reaction written with that cation, like so. In this case, our cation is sodium. And because our cation is there, it counterbalances the negative charge of the NH2 anion. So we do not need to write a charge on this. It's indeed a neutral compound now, NaNH2. Notice then also on the other side, the hydroxide, the OH, is also counterbalanced with the same cation. And again giving us a neutral compound, NaOH. Because it is there to balance out the negative charge, it is called a counterion. Now, as you can see, the counterion isn't relevant to this reaction. It's not really doing much. It is there just to balance out the negative charge. And so because it is quite irrelevant, sometimes you can see the reaction written without the counterion. So you just want to be able to recognize when it is present that it actually doesn't do much. Now let's take a look at this reaction beyond just a definition. Let's dive into the mechanism of an acid-base reaction. In this class, we will see many other types of mechanisms, so this is a good place to start to understand mechanism. The first thing about mechanism is that we will use curved arrows, the same curved arrows used in drawing resonance structures in the previous chapter. Now remember, when we used curved arrows back then, they were simply a tool for us to draw resonance structures. The arrows don't represent actual movements of electrons. However, when we draw curved arrows in mechanisms, they actually do represent the movement of electron densities, and they show the reaction mechanism, how the reaction occurs. As our starting point with the acid-base reaction, our curved arrows must show somehow that the proton on the acid is abstracted by the base. So remember, curved arrows must start from a source of electrons because you're showing where they're flowing to. So they either start from a bond or a lone pair. So in an acid-base reaction, the curved arrow starts from the lone pair on the base and heads towards the proton. You would need two curved arrows. You need the abstraction step and the bond breaking step. And here's why. Remember that the curved arrows represent where electrons are moving. If it acts as a lone pair and it's going towards a proton, that means it's donating its electron to that proton and therefore forming a bond. So with that one curved arrow, we would have a species that looks like this, which is highly unstable. For one, there's too many electrons on that middle hydrogen. It even has a negative charge. Remember, hydrogens can only form one bond. So if a new bond is formed with it, then it must break the old bond. So this bond must break, right? So in order to break a bond, what happens is we draw a curved arrow from that bond, and those electrons will be dumped onto the oxygen. So you draw it starting from the bond and ending at the oxygen. I'm being very careful and explicit here, so you may draw curved arrows properly, because if you draw where it starts and where it ends unmindfully, it may represent a totally different mechanism and a possibly wrong mechanism. So be very careful of where the arrow starts and where it ends. All right, so let's have some practice with this. All right, just given this equilibrium, can you identify the acid, the base, and the conjugate acid and the conjugate base? Notice the molecule with the ring structure loses a proton, right? So that must mean it is the acid. So if it is the acid, then its conjugate must be a base. All right? On the other reactant, the OH minus gains a proton, so it is a base, and its conjugate is an acid. So our next task is to draw the curved arrow notation for the mechanism of this acid-base reaction. So again, our base is going to abstract that proton. So we're going to start from the lone pair on our base and draw our arrows to end at that proton and breaking the bond connecting the proton to the original molecule. So two curved arrows there. All right, so let's go ahead and see another example. So in this equilibrium, we actually have only one molecule reacting with itself. It is both the acid and the base, where the acid-base reaction is happening within the same molecule. We call such a reaction an intramolecular proton transfer. The key word here is intramolecular. When something's happening between two different molecules, that's called intermolecular, right? So if it's happening within the same molecule, it's called intramolecular. So let's go ahead and draw the curved arrows for this reaction. Notice that the oxygen on the left there is negatively charged, and somehow, as a product, it has a proton. So that's going to be your site of your base. So it's going to abstract that proton and breaking that original bond. So we see that the oxygen on the left will act as a base, and the OH of that molecule will act as the acid. So let's go back to this example to explore a different definition of an acid and a base. The definition of the Lewis acid and base. As a foreshadow from our curved arrow mechanism, we pay a special attention to how the electrons are flowing in this reaction. The Lewis definition is primarily focused on this feature. And so in fact, the Lewis definition is based on the flow of electron density. In the Lewis definition, an acid is an electron pair acceptor, and the base is the electron pair donor. So in this example, we see that the electrons is flowing from the OH minus into the other molecule. So in a sense, the OH minus was once negative, and as a product is no longer negative, so less electron density, right? It somehow gave away its electron density. So what is an electron pair donor? That is a Lewis base. So in fact, the Branstad-Lowry base is also the Lewis base. And on the flip side, that Branstad-Lowry acid was once neutral, and as a product is negative, so it's gained some electron density. So what is a species that has accepted electron density, accepted an electron pair? It is a Lewis acid. Yes, so in fact, all Branstad-Lowry acids are Lewis acids, and all Branstad-Lowry bases are Lewis bases also. And the reverse is not true, because not all Lewis acid and bases can be Branstad-Lowry acid and bases. So here's an example of that instance. Notice that the reaction involves the lone pair of this water molecule donating its electrons towards this boron in this BF3 molecule, forming this new bond. Right? So in this definition, the water is donating its electron, so it is the base, whereas the BF3 is accepting the electron, so it is the acid. In this case, since there's no transfer of protons, you cannot call this a Branstad-Lowry acid or Branstad-Lowry base. Now let's get back to the Branstad and Lowry definitions of acids and bases, because when we talk about acid-base reaction, that's what we need to focus on. So we're going to take a look at it from a quantitative approach. Quantitative means dealing with the numbers. Now, this section could be a little bit review from you if you remember your stuff from general chemistry last semester. So to start off, remember that acid-base reactions are equilibria. So we're going to have a quantitative perspective to acid-base reaction. And why is this important? Well, when you are performing a reaction, for example, you want the reaction to go to completion. So you must be able to choose the proper acid-base reaction that is strong enough to push the reaction forward. So there will be two ways for us to approach identifying a strong versus a weak acid. In this section, we're going to go towards the quantitative approach. In another section, we'll take a look at a more qualitative approach. And really, when I say quantitative, we're really looking at what is known as a pKa. So let's take a step back and figure out where this pKa comes from. The Ka here is the acidity constant, and it is a quantifiable number used to rate the relative acidity of different compounds. And for a common base chosen for this comparison, we will use water. So let's take a look at an example. In this example, we have acetic acid and water as their base. The water abstracts the proton from the acetic acid, giving us the acetate ion and the hydronium ion. And it turns out this reaction doesn't go much to the right. When the reaction comes to equilibrium, you have a lot of the reactants left and a small amount of product. This is why acetic acid is considered a weak acid. But how weak? We can define this term using the equilibrium constant. The equilibrium constant is a ratio of the products over the reactants. So let's fill in this equilibrium constant. We're going to abbreviate a few things here. We're going to call acetic acid HA, and therefore the acetate ion A-. So the equation comes out to be the hydronium ion multiplied by acetate ion over the concentration of acetic acid, water. So it turns out because we are in aqueous solutions, there is a copious amount of water. So water's concentration will not change as much. So because it doesn't change, we can move it over to the constant side. If we multiply both sides by the concentration of water, we get a new equation, which is the hydronium ion concentration times the concentration of the conjugate base, A-, divided by the concentration of the acid, HA, will give us a new constant we call Ka, the acidity constant. Notice that if your reaction proceeded forward, meaning you have a lot of products at equilibrium, then your numerator will be a larger number than your denominator. In that case, then the Ka value is going to be a very, very large number. On the other hand, if you have a reaction that doesn't go forward, but actually at equilibrium favors the reactant side, then your denominator, the acid, will be large, much larger than your numerator, right? So because of that, you will have a very, very small number, a fraction. So if your Ka is a very, very small number, usually 10 to the negative power, then you are going to be a weak acid, versus if your Ka is very large, 10 to the power of a positive number, then you will be a very strong acid. And this range could be from 10 to negative 50 to 10 to the positive 10. So it turns out in this example, acetic acid has a Ka of 1.75 times 10 to the negative 5. That's a mouthful, right? So that we'd have to say all of that whenever we talk about acidity, we come up with something called the pKa. The P is basically stands for the negative log. So pKa is the negative log of Ka. So if you go ahead and take the negative log of that, we will see that it comes out to be 4.8. So we say that the pKa of acetic acid is 4.8. It turns out that the range of pKa is from negative 10 to positive 50. Let's take a look at some functional groups and their pKa's. We're going to start from the strongest acids down to the weakest acids. Remember the R here just means an alkyl chain, a non-descriptive carbon-hydrogen chain. So the strongest acids we see here are the hydronium ions, protonated alcohols, and protonated ketones. They have a pK of around 0. Notice the trends here. They all have that formal charge, and so that proton is very susceptible to being abstracted off. Okay, so our next one here is carboxylic acid, the one that we just saw. I like to remember it more roundly, so I'm going to remember it as around 5. Our next group here will be the thiols, the phenols, and the protonated amines. They all have a pK of about 10. And then there's water or the related alcohol. I like to remember these having pKs around 15. Of course, there will be slight differences. These are just approximate pKa's. Let's continue our list in the second column here. The first one is the hydrogen off of a terminal alkyne. It has a pK about 25. How about the alkene proton? That has a pK about 45. And then lastly here, a simple alkane would have a pK of around 50. So there's some trends here, and we'll talk about these trends in another video. I also want to plug in here where amines would be. A non-protonated amine would have a pK around 40. So now that we have this value called the pKa, let's see how we can use them. The first thing we can use the pKa values for is to compare the relative acidity between two acids. For example, if you were given these two molecules and their pKa's, you should be able to determine which one is the more acidic molecule. As we said before, the lower your pKa translates to a higher Ka, which means more products, which ultimately means that you are more acidic. And so in this case, the first molecule here with the pK of 4.75 would be the more acidic molecule. We can also use pKa to compare relative basicity. For example, if you were given these two molecules, which one is more basic? To answer this question, imagine what is its conjugate acid and what is the pK of that conjugate acid. Comparing the conjugate acids, which one is the stronger acid? Between these two conjugate acids, the alkyne will be your stronger acid. Remember the seesaw effect? If the acid is strong, then its conjugate will be relatively weak, whereas if the acid is weak, then its conjugate will be strong. And since amine is the weaker acid, so its conjugate base will be the stronger base. So that's how you can use pK to both compare the relative acidity of two compounds or the relative basicity of two compounds. We can also use pKa's to predict the position of equilibrium of a reaction. For example, if you were given this equilibrium and asked to predict whether it favors the forward reaction or the reverse reaction, how would you go about doing this? So first step is you want to be able to identify the acid and the base in this reaction. So from the previous section, we have learned to identify that the first species here is the base, and this will be your acid. So the protonated base then will be your conjugate acid, and the hydroxide on your product side will be your conjugate base. Now you want to go ahead and locate all your acids. And if pKa's are given to you, then great, go ahead and use that. If not, then you can use the approximate pKa's that you have memorized. In this case, let's say it was given to us. So in this situation, it turns out you can use a mathematical relationship for the equilibrium which states that the KEQ is equal to 10 raised to the difference in the pKa, which is the pK of the product minus the pK of the reactant. In this case, that's 18 minus 15.7, which is 10 to the power of 2.3. So again, this is your KEQ. If your KEQ is a very, very large number, in this case 10 to the positive power, what does that mean again? That means that your product is heavily favored, right? So your numerator is a larger quantity than your denominator. So in that case, if product is favored, then the reaction is pushed towards the right at equilibrium, or you can say product side. So I want to show you a quick way of also doing that. And the quick way is, again, just to locate between the two acids which one is your stronger acid. In this case, it's on your reactant side. So if your reactant side is a stronger acid, then it will dominate being an acid. And so as being an acid, it will react with the base, pushing it towards the right-hand side. So the reaction always goes towards the weaker acid. So that's a quick way of doing that. Let's use that strategy in the next example. Let's say you propose to deprotonate this amine with this alkylamide ion. Will this reaction proceed forward? Okay, again, identify your acids and their pKa's. Let's say in this case, pKa's weren't given to us, it's just based from our memory. Then I would say from memory, the pK of an amine is around 40, the pK of an alkyne is around 25. Okay, so because of that, the alkyne is a stronger acid. And if the stronger acid is in your product, then it's going to push your equilibrium to the left. So in this equilibrium, the reactants are favored. From an application perspective, then, you would not want to use this anion to deprotonate the amine. And the last aspect of the application side that I want to discuss is that using pKa's, it can help us choose the proper reagent for acid-base reaction. And then also I want to touch base on something called the leveling effect. So let's first start with the choice reagents when you want to perform an acid-base reaction. So as a given, when you perform a reaction, you want it to go to completion. You want to make the product. You don't want just to have your reactants left over, right? So you want it to favor the product side. You want it to go in the forward direction. So your choice of acid or base is very important to push your reaction to completion as much as possible. Let's say you want to deprotonate this molecule, which has a pK, again, is an alcohol, so around 15. So which reagent will you use to deprotonate this molecule? And specifically, which base would you use? And it turns out you want to choose a base that has a conjugate acid with a higher pKa than the acid that you want to react with. So let's say, for example, you want to use ammonia to deprotonate this molecule. Will this reaction work? All right, so remember, your base is ammonia here, and its conjugate base would be this protonated ammonium ion. What's the pK of this protonated ammonium ion? We said it was around 10, right? So which is a lower pKa than 15. So actually this will not work. Again, from the equilibrium perspective, why is this? Remember that the pKa of your ethanol is 15. So comparing the two acids, the ammonium ion is a stronger acid, so it will push your reaction to the left, towards the reactant side. So this is a no-go. All right, so what is that base that has a conjugate acid with a higher pKa? What about an alkylamide ion, a deprotonated alkyne molecule? Will this work? Remember, the pK of this molecule is 25, so it is larger than 15. So this probably will work. Let's do the analysis here. Again, the alcohol is pK of 15, so it is a stronger acid than the alkyne with the pK of 25. So it will dominate this reaction, pushing the reaction to your right, favoring the product side. So indeed, if you wanted to deprotonate this alcohol, you do want to use the alkylamide ion. Forgot that negative charge is there for the alkylamide ion. Speaking of that negative charge, remember, from a practical perspective, you can't just have ions in there. You will need a counter ion. Sometimes you will see this with its sodium counter ion. All right, let's do another example of this effect. Will NaOH be strong enough to deprotonate this ketone? And this ketone has a pKa of 19.2. NaOH, again, is just the hydroxide there, is your reactant. The sodium is just your counter ion, so we can ignore that. And we don't know if this reaction will occur, but if it did, what would the product be? There's only one site where a proton can be deprotonated. It is at that carbon position, and then the other product, of course, will be water once OH is protonated. All right, let's consider the equilibrium here. Again, when we want to consider equilibrium, we want to take a look at the two acids and compare which one is a stronger acid. In this case, the acid is the ketone on the left, and on the right, it is the water. All right, because water is the conjugate acid of that OH minus. All right, so again, what's the pKa here? It was given to us that the pKa of this ketone is 19.2, whereas the pKa of water, we know, is around 15. Again, just ballpark there. So will this reaction go forward? It will not, right? Because the acid on the product side is much stronger. So it's going to push the reactant to the left side, favoring the reactant. So this reaction is a no-go. So as a follow-up question then is, can you suggest a base that will make this reaction go forward? We want to use a base with a conjugate acid that is larger than 19.2. Okay, so what would that be? Again, can we use the base of that deprotonated alkyne? Remember, because an alkyne has a pKa of 25, which is greater than 19, right? So it probably will. So let's take a look at that example. Will it go forward? Again, this is your acid here, and its pK is 25 versus 19.2. So the ketone here will be your stronger acid, pushing the reaction to the right hand, favoring the product. So again, this will be a wise choice. Let's now move on to talking about the leveling effect, which discusses how the solvent can participate in a reaction. So again, let's just focus on the example that we just went over. We said that indeed the base that we chose could drive this reaction forward. However, now let's talk about the solvents we can use. Can water be used as a solvent in this system? So remember, if something is a solvent, it's going to be the predominant species. It's going to be the bulk amount. So you might have to consider if it would interfere in the reaction that you have intended. So your intended purpose is for this base to react with your acid. However, if water is in your reaction vessel, it can also react with your base. So water can act as your acid too. So sure, both of these reactions can happen, but remember that water is so much around that the chances of it reacting with water is higher than it can react with your acid of interest. Because of this, all of your base is basically sucked up in reaction with water, leaving you with OH minus as the next strongest base around. So now all you have as a source for this base is this hydroxide ion. We have just established before that this hydroxide ion is not strong enough to deprotonate this ketone. So in essence, you set out to deprotonate this ketone, but however, all of your base is sucked up by your solvent, so nothing is available to perform the acid-base reactions that you intended. So this, in essence, is the leveling effect, that the strength of the base is limited by your solvent. It will be as strong as a base as the conjugate base of your solvent. So this is important to consider when you are designing an experiment, to choose the proper solvent, that it does not diminish the capacity of your base. This effect, of course, can also affect acids. So again, to summarize, this is called the leveling effect, where the solvent reacts with the strong acid or base instead of the reactants of interest. So that ends our discussion of acid-base reactions, looking at it from a quantitative perspective. In our next video, we'll take a look at the Branstad-Lowry acid-base reactions from a more qualitative perspective.